Good morning, Year 11. This is your whole class feedback for the nuclear radiation past paper questions that you completed last week. On the left here, we have some common issues that I've noticed as I've gone through looking at everybody's paper. If you take a moment, you can go and look through your own paper and see which one of these you think applies to you. Pause the video while you do that. On the right hand side, you'll notice the dirt activities that I would like you to complete. Everyone should complete the consolidate task, making sure that your answers were correct for the past paper questions, improving them as you go using this video. Once you've done that, I'd like most people to complete the develop task. Go back to the mastery booklet and attempt more questions to improve your understanding of any topics that you didn't do well on in the past paper questions. If you got almost 100%, I'd understand why you would want to skip this step. That's why there is a stretch dirt activity. It's a research task. It will require you to go into significantly more depth than is required for GCSE. This is partly aimed at those who are interested in studying science further at A-level and beyond. Question 1. Question 1 makes you identify radioactive sources based on their penetrating power, what they can go through. Now, a common problem here was not picking up that of these options, ultraviolet is not a form of nuclear radiation. Ultraviolet is ionizing, but it doesn't come from the nucleus. So for these style of questions, ultraviolet will never be an option. A travels through thin paper, but not thin metal, so it must be beta. B travels through thin metal, but not thick lead, so it must be gamma. And C travels through, well, nothing, so it is alpha. In question 2, you have to identify which of these are isotopes. A common mistake was to start talking about electron structure. The problem with talking about electron structure is that atoms can lose or gain electrons, so it doesn't tell us anything about which of these are isotopes. You have to consider only the particles in the nucleus. So, which of these are isotopes? Well, in this case, the dark spots represent protons and the light spots represent neutrons. So isotopes are the same element, they have the same number of protons. Therefore, Y and Z are isotopes. Question 2b is about explaining the classic Rutherford gold foil experiment. It's important to notice that there are specific instructions. First of all, that you need to use good English. So this is partly a quality of written communication question. And secondly, you have to explain all 3 of the different paths if you want to get full marks. So, path A. Path A passes through the atom without deflection. Why? Because it passes a long way from the nucleus. Alpha particle B is deflected by the nucleus because it has the same charge as the nucleus, so it is repelled. And then finally, alpha particle C is also deflected by the nucleus straight back along the path that it came in along. Question 3 starts out very, very simply with the definition of beta radiation. Beta radiation consists of an electron. You might have added extra detail and said it consists of a fast-moving electron. That's good, but not required to get the single mark. The second part was poorly answered, and that was partly because of a typo in the question. I don't think anyone noticed this typo, but clearly it says when atoms of uranium-238, but then say that it's uranium-234. That's incorrect. And then Further down, where the question actually is, it says thorium-234, but then has thorium-238 in the question. Apologies for that. I don't know why that occurred. So what differences are there between a nucleus of practinium-234 and a nucleus of thorium-234? Well, they have the same mass number, so they have the same number of nucleons, protons and neutrons together. However, we formed practinium from thorium by beta decay. And beta decay reduces the number of neutrons by 1 and increases the number of protons by 1. So the practinium atom, the practinium nucleus, has 1 additional proton and 1 fewer neutrons. Question 4 was poorly answered generally. It's because it has a confusing and unusual context. You've never been taught about a spark counter, but you have been given all the information you need in the question. When a charged particle passes through the gap between the wires, a spark is seen. Give the name and symbols of 2 particles that will cause a spark. So we're just looking for 2 particles that are charged. Because this is a question about radioactivity, we're looking for 2 forms of nuclear radiation that are charged. Some people said ions of some sort. So they said, for example, a carbon ion. Now, that is true, but we need to think carefully about what the question is likely to be asking us. It's about nuclear radiation. It's asking us for forms of nuclear radiation. So we're looking for alpha and beta radiation. For the symbols, we need to be a little bit careful. If we're looking at the symbol for an alpha particle, it's not the same as a helium atom. It's a helium 2+ ion. For beta, it is just an electron. And if we're being precise, we should also put in the minus sign. E-. That should really be superscript as well. The numbers, the AZ numbers, the numbers of protons and neutrons in these things are not required in this case. Part B is just a question about penetrating power again. A piece of paper is slid between the source and the counter. The sparking stops. What kind of radiation is being stopped by paper? It's alpha. Part BII was sometimes not brilliantly answered. When you think what will happen once we've removed the paper and we slowly move the source away from the spark counter. So as the range increases, the number of detected alpha particles will go down because there's a short range in air. So the number of sparks will fall, and then once we get above the range of alpha in air, it will fall to 0, or at least fall to the same rate that it would have just due to background radiation. Question C. A radioactive source gave a high reading using a Geiger-Müller tube and counter, but did not cause sparking when brought near to the spark counter. Why? We're looking for a form of nuclear radiation that is not charged or is not ionizing. So it is a gamma source. Gamma is not ionizing, nor is it charged, so it will not cause a spark. Question 5 is actually a fairly classic half-life question. Again, the context is unusual, and lots of people drop marks because they didn't attempt questions that they could have done if the context hadn't been unusual. The first part of this question is just to try to determine the half-life of uranium-238. Note that you have to show how you obtained your answer to get full marks. How are we going to do this? Well, we're going to read off the starting radiation emitted, the starting count, halve it, and then draw a line across from that half value. So in this case, we are going to carefully, and this is important, carefully measure the starting count. That is 48 counts per minute. So we're going to have to halve that to get exactly 24 counts per minute, and then draw a horizontal line across to our decay curve. I'll make that a bit thicker so you can see it. Something like that. As soon as we've done that, we can then draw a line down from the point that it intersects the curve, and we have our half-life. Hopefully you can see that the half-life is about 4.4 billion years. Part B gives us a very good clue that our answer to Part A is correct. What fraction will have decayed after 9 billion years? 9 billion years is very close to being 2 half-lives. So after 2 half-lives, we have halved twice, so we've gone down to a total of 1/4 of the total number of atoms that we started with. But the question asks, what fraction has decayed? So actually it's 3/4 have decayed already. Part C is about decay chains. Why are the intermediate radionuclides not important when estimating the age of the rock? Well, they are very short-lived compared to the half-lives of uranium or lead. Many people struggled with Part CII, estimating the age of the rock. If there are 3 atoms of uranium-238 for every atom of lead, then it has dropped to 3/4 of its original number of uranium atoms. There were 4 atoms of uranium, now there are 3 atoms of uranium and 1 atom of lead. So we need to go back to our graph. We started off at 48 counts per minute. So if we have 3/4 of the total amount of uranium left, then we have 3/4 the activity. So 48 divided by 4 times 3. That's 36 counts per minute. So just like before, we need to read across from 36. I need to concentrate to get this right. 30, 36. Making sure it's vertical. Something like that. And then we read down, just like we did before. And we should come out at roughly 1.6 billion years. Question 6 was a reasonably straightforward decay equation balancing question. It helpfully reminded us what the numbers were for an alpha particle and just asked us to reproduce it for a different decay equation. Part B was very, very similar, but for a beta decay instead. So this is the marks game. You can see that you are getting a mark for correctly copying across the alpha particle, correctly identifying the different nucleon numbers, and then also for identifying that you produce radon. Similarly for Part B, 1 mark for everything that is in the circles. Part C is for identifying what's happening in this decay diagram. We should be able to see that every time we go down and to the left, we're reducing the number of protons by 2 and reducing the number of nucleons by 4. So every time we go down from A to B, D to E, E to F, F to G, G to H, and J to K, these are all alpha decays. When we go horizontally to the right, the nuclear number is not changing. The number of protons is going up by 1. So this is a beta decay. B to C, C to D, H to I, and I to J. All beta decays. And then finally, why does a rock sample contain a large quantity of A, almost none of B through J, and a very large number of lead-208 particles? Well, the half-life of thorium-323 is billions of years. So that means that there will still be many thorium atoms remaining. Because the rock is very old, many more billions of years than the half-life, that means that there will be a large number of lead-208 nuclei, because many half-lives have passed. There'll only be tiny quantities of all of the other isotopes, because they have very, very short half-lives compared to thorium or the lead. Good. Now that you've completed all of those corrections and improvements, please attempt the develop or stretch tasks. If you complete the stretch task, and this is aimed significantly at those who are planning on doing physics next year, please can you submit it via Teams